Good evening, everyone. Let us get started with today's session. So we will start with a quick review of what we were discussing over the last week, and then we will be discussing about NSEA2. We will actually see one implementation of how actually we code it using Colab, and then we will see what is the effect of some of the parameters like the crossover parameter and mutation rate and all this on the convergence rate of NSEA. And after completing that, we will see into the strength Pareto evolutionary algorithm as well. So we were discussing about multi-object optimization. So we were discussing about the two different classes of methods. The one is the preference based.
अभी तो 4 लोग
Yeah, preference based method, and the second one is the evolutionary methods or our easy techniques. So we discussed that the main difference between both of these methods lies in the way we solve the problem. When we are having different objective functions in preference space, we kind of develop some kind of a weight method which will convert the multi-objective to a single objective problem, and then we solve it. And in evolutionary computation, we discussed about something called a Pareto optimal front. So we will try to get Pareto solutions, and once we get the Pareto solutions, out of them we use some high level information to decide which one of them is our optimal one. So we also discussed in the last week about some of the classical techniques versus evolutionary technique. The classical techniques, before going to the classical techniques, we will see what when we were discussing about the Pareto solutions. So we came across two terms. Basically, one is the dominance. The second one is diversity. So these are essentially, we discussed that we need both of these to be present in our Pareto solutions. Dominance is essentially if you have two solutions, say P and Q, and you have say M objectives. We say P is dominating Q. I'm using this less than symbol to say like P is dominating Q if it has to satisfy the two criteria that any questions? If you're not speaking, can you please mute yourself? Yeah, so we say if you want to compare two solutions to check for the dominance, essentially we say like for each of the objective functions, say if you have M objective functions, we need the value of P to be no worse than all the solutions in Q, or essentially if you have objective F1 calculated for P should be less than F1 calculated for Q, or it should be true for any objective function you are taking. It should be no worse in the sense it should be less than or equal to any objective function calculated at the value of Q, and there should exist at least one particular objective function where it is strictly less than, say there exists one I belongs to this set from 1 to M such that when you calculate the value of P, it should be strictly less than the value of, for the same objective function calculated for the solution Q. If these two criteria are satisfied, then we say P is actually dominating Q. And then we kind of said that Pareto optimal solutions is just the locus of all the non-dominated solutions. Once we get all the solutions and we check for dominance against each of these pairs, and then we collect all the points which are not dominating each other, the locus of all these points is what we call the Pareto front. So our entire objective in this particular approaches is to get all the solutions on the Pareto front. And we said like in addition to dominance, we need something called a diversity, which is when you have a set of solutions, they should be far apart from each other. Just to give you an
Sir,
example.
please explain strictly dominance criteria again.
Yeah. So
Two numbers.
second point, this one, right?
Yeah. Yeah.
So it is essentially saying, say you have, let's take one example. Say you have some function, bi-objective function, and you have two solutions P and Q. If you have something like this, or say something like this. Now, when you are comparing P and Q to check for dominance, what the second criteria is saying is there should be at least one objective function in which one is actually strictly better than the other. So, if you see here, F1 for P is less than F1 for Q. So, this if this exists for at least one of the objective functions, then along with and for all the other functions they should be less than or equal to, then you say it is dominating the other solution. If it so happens that both of them are equal, if both of them are equal, something like this, then it doesn't satisfy this dominance criteria, because it doesn't satisfy the second one.
So both F1 and F2.
Yeah, or it can happen the other way as well. Say something like this is 0.4, this is 0.3. If you have something like this, in this particular case, if you see like F1P is actually equal to F1Q, and F2P is actually greater than F2Q. So like here, you cannot say which one of them is actually dominating the other or not. So there exists no relationship between P and Q, right?
No, in here, P F2 for both P and Q, F2 at P is more than at F2 at Q.
Yes.
Only F1 is same.
Yeah, only if F1 is same. In that particular case, you cannot say that P is dominating Q.
Okay. Both should be satisfied.
It should satisfy in this strict inequality in at least one of the objective functions, and less than or equal to in all of the objective functions. Only then you say P is dominating Q.
So in this example, whatever you have written, P at P point, F1 is 0.2, F2 is 0.4, Q is 0.2 and 0.3.
Yes.
So is it eligible for strict this thing, strict dominance?
No, these are not dominating. Here P is not dominating Q.
It is not a minimum.
That is not a minimum. You can like if you just see the
But
values.
we can say Q is. But can we?
If you put it the other way around,
Q is dominating P.
Yeah, if you put it the other way around, then it works. Like here, Q is actually dominating P. If you were to say between P and Q, there is no relation, but Q is dominating P, because F2 of Q is actually less than F2 of P, and there exists an equality as well.
But we can say P is dominated by Q.
Yeah, both are okay. Q is dominating P, or P is
P is
dominated
by Q.
Yeah, fine.
Okay. Suppose both are equal. It is all are 0.2.
Something like this. All are point or something like this is also fine. So you are saying both F1P equal to F1Q and F2P equal to F2Q.
Right.
Yeah, if you have something like this, then also they are not dominating. Because
they are not dominating each other. Yes.
Yeah, they are not dominating each other. Like such kind of solution should not be in your Pareto.
Okay.
Fine.
Yeah.
So after we discussed about this Pareto front, then we discussed about some of the classical methods. We discussed about first we discussed about the weight sum method. So we told you have some, say if you have a bi-objective function in essentially two objective functions, you define a new function capital F that is a weight combination of f1 and f2. It's a weight combination of f1 and f2. Then we kind of try to minimize this capital F, and then for each value of w1 w2 we will get different solutions. So if this is your objective space, your aim is to minimize both f1 and f2. We kind of derived in the last session that if you try to minimize the value of f, dou f dou f1 should be 0 as well as dou f by dou f2 should be 0. If you try to do that, then for what we essentially end up is having a tangent at that particular point. So for each value of w1 w2 you will be essentially ending up with different tangents, and so that you will enter in essence you will be covering so many points at each of these tangents, and all these points combined will give you the Pareto front. And we also discussed that since this is only each value of w1 and w2 are not kind of independent from each other, like we have a relation between both of them, that w1 and w2, like sum of them should be equal to 1. So if you fix a value of w1, then w2 is kind of constrained from that, and so once you fix the w1, then the slope of this particular tangent is fixed, so you will be getting 1 point on the Pareto front. So this particular method, as we discussed, is not suitable if you have something called a concave fronts. So if you have something like this, then it can so happen that 2 points can actually pass through the same tangent. Yeah, something like this could also happen. So for the same value of w1, the same tangent, it can actually touch the Pareto front, can touch your objective space at two different points, and in that particular case you cannot be sure that which one of them is actually your solution. So we told like okay, this particular method is only suitable for the Pareto fronts which are of this particular kind. So we call this, say, convex.
Excuse me.
Yeah.
These weights of W and W2.
Yeah.
Sum is W1 plus W2 is equal to 1. Can any of these things can be taken 0?
Yeah. You can take w1 to be 0, then w2 will be 1. w1 and basically they range from 0 to 1.
Then it will not be.
You won't be end up taking one.
Multi-objective.
Sorry?
Yeah, then it will not be multi-objective.
No. We will continuously vary w. Say first you take a w1 of like you will not do it for just one w1. You will have so many w1s. Say you have some index, some w1. So for the first iteration, maybe when you solve for the first time, you will take a w1 of say 0.2. The next time you take w1 of 0.4, and then you do it like 10 times. You get all the values or all the possible w's. For all these, each of these w, you will get a different solution, right? And each of that solution will be one of the minima for that particular object, and that will be on the Pareto front. So when you combine all these solutions, then you will get the entire Pareto front.
So by definition, this to get the Pareto front, this W and W2 should be non-zero.
No, right? There can be
this
solution.
Should be non-zero.
No. There is no condition like
because
it has to be non-zero.
Then it will become. Pardon?
If you take 0 only for that particular scenario, you will be getting one minima and you will not be using. But that could also be one of the solution, right? In your Pareto front.
No, in Pareto front, both should satisfy, na? Both minima should satisfy.
Both minima should satisfy. Yeah.
Otherwise, it will be stream.
Okay, let us take the example we were discussing previously in the last week. So we were discussing this particular function, if you remember. So we have to
Yeah.
minimize minus x, and we have f equal to x square plus y square, that we want to minimize both of these functions. So we kind of got a solution. If you try to minimize this particular solution, you got the stationary points to be w1 by 2 times 1 minus w1. So you are saying if I take w1
Mm.
to be 0, the stationary point will correspond to 0 comma 0, and that is also on the Pareto front. Like even 0 comma 0 lies on the Pareto front, right? In this particular case.
Okay.
Is that what you are asking?
But
Like you are essentially saying if I put w1 equal to 0,
actually, in in one of the book, I have that W1, W2 are non-zero.
yeah,
That's why I was
both of
wondering
them
if
are not 0 at the same time.
no, both of them cannot be
Yeah, that happens comes from directly from
zero,
this relation. If you put one of them to be 0, the other one will be 1. So both cannot be 0 at the same time.
but one can be zero.
Yeah, one can be 0, right? Like you can see in this particular case we have solved previously. If one of them is 0, the other one will go to 1. So that will give you one solution.
Mm-hmm.
Like continuously
That will
vary,
be the
that will be
stationary
just
point.
one point. You
Yeah.
continuously vary w1, you will get so many other points, and once you plot all of them, you will get the entire Pareto front.
Mhm.
Clear?
Okay.
Okay. Yeah, so we were saying like this particular method is only suitable for this type of convex fronts. So when you have a concave front, this particular method is not applicable. It is essentially because you are having, when you are trying to solve the problem, you are only solving for a tangent. So in order to kind of come across this particular limitation, the next method is the epsilon constraint method. What we essentially try to do in this particular method is instead of trying to get a tangent, we will fix this line to be a straight line. So if you were to take the same, instead of the tangent, we will take a straight line now. And this will be my particular value of epsilon that I will vary. So for once I fix a value of say one of these objective functions, say f1 equal to epsilon, and see how you will get the minimum value for, in this particular case, the minimum value is somewhere here. Now what I will do, I will change the value of epsilon again. So when I change the value of epsilon, the new minimum will be somewhere over here. And I'll keep on doing this, like I will vary epsilon continuously till the other end of the objective function to get all these minimal points. And once I combine all these minimal points, the entire solution will give me the Pareto front. This is the idea in the epsilon constraint method. So here you can see like for each value of epsilon you will get only one solution, like one minimum for that. But in the previous case, like even for one particular value of w1, there is a possibility that you get two different solutions. So there you cannot rest assured, like in the Wayne method, like you cannot be sure whether you are getting a unique solution or not. But here you can be say, you can say for sure that you will get a unique solution for each value of epsilon. This is one of the advantages, but the way we formulated the problem in this is a slightly different from the previous case. Like in the previous case, when we said f equal to w1 f1 plus w2 f2, we kind of just solved two equations, del f by del f1 and del f by del f2 equal to 0. But now in the epsilon constraint method, what we are essentially trying to do is instead of two objectives, we will only solve for a single objective function. So instead of minimizing f1 and f2, what we will do is only minimize f2 and pose the second one in type of a constraint. Subject like f1 is less than or equal to epsilon, or f1 is greater than or equal, depending on your type of problem. You are converting your multi-objective problem into a single objective problem, and all the m minus one. Say if you have m objective functions, you are converting them into a single objective function. This will be your objective function, and remaining m minus one will be your constraints. So when you are having all these constraints, like if you have a single objective function and there are a set of constraints, then you need to solve it using the KKT conditions. You have to apply all the KKT conditions and then solve each one of them. So that will increase the complexity of your problem. So this is one of the drawbacks with this particular method. And then we also discussed some another method called Chebyshev method. So the idea there was, if your aim is to minimize both the objective functions, there is something called an objective vector we discussed. That objective vector is essentially ideally the minimal point that you would get if both f1 and f2 are not dependent on each other. In the sense, if I just minimize f1 without considering f2, then I would get a minimum of somewhere here. And if I try to minimize only f2 without considering f1, then I would get something somewhere over there. So the point of intersection of these two, like the point of intersection of both of these, is something we defined as the ideal objective vector. And this may not actually lie in your feasible space. Like this entire thing is your feasible space. Ideal objective vector may not lie in your feasible space. Like it may lie if your f1 and f2 are not conflicting with each other, then it may actually be the only solution. But usually f1 and f2 will be contradicting with each other. So your ideal objective vector will be lying outside your feasible space. So what we discussed is like you take some of these points, and what you do is to convert your optimization problem into a minimization problem in such a way that if you any point that is considered inside, so if you consider any point inside, the distance from that particular point to your ideal objective vector is to be minimized. So now our objective function will be something like this. So your original problem from minimize f1 and f2 is now reduced to another single objective problem, where you will take a weight combination of all of these such that you minimize the distance. Say I am using the distance as, or we can actually write the Euclidean distance. That particular point, if I am denoting by z minus z star, to kind of iterate over all the objectives. So here we have only two, so you only do for those two. So basically you try to minimize the distance between this particular point and this thing, like ideal objective vector. You can have different cases, like I have written only for the Chebyshev method, but ideally you can have any, say, wi into the particular value of z minus z star whole power p power 1 by p. So this p will determine your power. Basically, if you want to have an Euclidean distance, or if you want a Euclidean distance, you have p equal to 2. You can kind of take all the different kinds of distance. If you say p equal to 1, then it will be similar to our original case of weight sum method. As you gradually keep, if you take p equal to infinity, that is what you call the Chebyshev method. There is another method we discussed. Instead of taking the ideal objective vector, we could pose a problem in a different way. Say,
here you have to minimize L.
Yeah, you have to minimize L. L is basically this distance. When you try to minimize this L, this point over here will gradually move towards the Pareto front, right?
And this W is same weight?
W's are similar to the weight sum method. They are the weights that you will be changing to get different
Weights.
solutions. Yeah, they are the weights. You change those weights to get different solutions. Like each value of W will only give you 1 point on the Pareto front.
Okay, here also W can be 0?
Yeah, it's the same, 0 to 1.
0 to 1. And it will be positive.
Yeah, 0 to 1 is positive, right?
This will be positive only.
Yeah, 0 to 1 is positive.
Yeah.
If you try to keep negative constraints, then like, see, our idea is to minimize the value of L, right? So if you have some negative constraint, if you put some negative weight in that, it will try to increase the value of that particular, whatever is there in that quantity, right? That is not what we want. So
okay.
You just need to have positive weights.
So if I want to maximize some function, then we can take negative value.
That's the duality principle, right? If you want to maximize some function, what you pose a problem in a different way, say you minimize the negative value of that function.
Okay.
So if you do not do that, then essentially the weight becomes negative.
Means EC are for minimization.
Sorry, I didn't.
We can convert maximization problem to minimization.
Yeah. We were discussing only minimization problems here, but if you have a maximization, you convert it to minimization and then you can solve.
Yeah, yeah. I mean, this easy methods are only for minimization.
No, they are not only for minimization.
Basically.
You can kind of adapt to them whatever you want. If you want to maximize, then
Means, yeah, yeah.
you have to
That is
just change
converted to be
accordingly.
converted.
Yeah,
Ah,
that's it.
okay.
Yeah.
Thank you.
After this method, we also discussed about the Benson method, where the idea is slightly different. Instead of trying to find one point outside and trying to get close to the point, what we will say is take a point inside the feasible region itself and try to move any solution away from this particular point. So when you have different solutions inside the region, what we say is you try to maximize the distance between this. Like here it will be a maximization problem where you will try to maximize the distance between any point versus the point you have chosen. What eventually will happen is, since this point is inside the feasible region, if you try to maximize the distance from that particular point, it will gradually move towards the Pareto front. That is the Benson's method. Once we discussed all these methods, then we talk like the idea here is like you take one particular weight and like one particular set of weights and you get one solution, and you take different values of w's will give you different solutions. Instead of doing that, we have something called, in our evolutionary techniques, we have the population. Like your different weights will correspond essentially to different individuals in your population. So if at your convergence, what you essentially want is each of these individuals should go and join one particular value of on the Pareto front. So we need to have a fitness function that will kind of drive our optimization in that direction. So we discussed for that, basically your fitness uh, in a single objective case, our fitness essentially has only the objective function. But now in this particular case, when you have multiple objective functions, just giving a value of objective function will not be sufficient. Uh, Say when you have these are all when, say if this is your objective space, and these are essentially the Pareto fronts. Pareto fronts in the sense of different, we discussed about the concept of rank, where you kind of say in this particular, whatever solutions that are lying on this particular line are all non-dominated, and when you have say these are all of rank 1, and when you take the second set of solutions, they are of rank 2. So any solution on the curve of rank 2 is essentially dominated by the solutions on the rank 1. So we need to somehow keep this information into the fitness function, so that when we solve our optimization, the evolutionary technique will kind of converge to solutions where we have ideally all the solutions to be only in the rank 1. So all these solutions will gradually move from the second front to the first front. That is what our objective is. So this will be our like the fitness should somehow keep this information into it. So it need to have some information about the rank. And the other metric we defined was the diversity. We told like when you have a Pareto front, we don't want all the solutions to be in one narrow region of it. So if this is your Pareto front, I don't want my solutions to be too close to each other. I want them to be spanning across the entire length of the Pareto front. So that we quantified using the diversity metric. So all these three things should somehow be incorporated into our fitness function. Only then we will be able to apply our easy technique to solve one of these optimization problems. So one of the algorithm we started discussing in the last week is the NSCA, non-dominated sorting genetic algorithm. So we'll take up the same problem that we were discussing previously, but then solve it using a genetic algorithm. So this is our problem. You need to minimize the first function minus x, and your second function is x square plus y square, subjected to this particular constraint that x and y less than or equal to 1. We are considering a population size of 8. The first step is essentially to initialize your population. Say this is how you, like these are some random initializations, you get the values of x. And next you evaluate the objective function values for all these x and y. So when you substitute the value of f1 and f2, these are the values I get. Like f1 is essentially minus x, so this is my x, and f1 will be essentially negative of that, and f2 is essentially x square plus y square. So once I evaluate the function values, the next step is essentially the sorting. Basically when you want to assign the fitness, so this is the algorithm which we started discussing in the last week. So we told if you directly want to sort your entire solutions and get the rank of each individual, it would take the algorithm to have an order of mn cube. So the main idea in NSEA is essentially to reduce this complexity from mn cube to mn square. And how they did this is essentially using this particular algorithm. So what they were trying to do, we will solve it using an example to understand this algorithm. So the first one they are saying is for each p belongs to capital P, this capital P is your set of solutions in original parent population. So all these things will be my capital P, and small p is essentially your index of that particular individual in the population. So first step is essentially for each individual you define something called SP, that equals to phi is your empty set, null set, and NP is essentially equal to 0. So I am just defining an S value here. I will keep on adding the values as you iterate over the values of P. So like P equal to 1 will be essentially S1 equal to phi is this particular individual, and then N will be 0 for all the individuals. So I have 8 individuals, so I have just kept 8 zeros. So your P ranges from 1 to 8 and your Q ranges from 1 to 8. That is your second loop. For each Q belongs to P. So like both of them are belonging to P. So Q also ranges from 1 to 8. So the first step is if P is less than Q. So when I just put all these values, let us compare each one of them. So as we discussed, if you want to compare P and Q, we essentially told there are two criteria. First criteria says for each of the objective function, fm of P should be less than fm of Q. This should happen less than or equal to fm of Q for all m belongs to 1 comma m. And then we told like there should exist at least one value belonging to this particular objectives where is strictly less than fi of Q. Only if these two criteria are satisfied, we are saying P is dominating Q, like it comes into this particular value. Now if you see the first solution, like if you want to compare 1 with only 1, like our first case is P and Q both are equal to 1. If you want to compare 1 with 1, both the values of F1 and F2 will be equal to each other. Both of them will be equal to each other. So this criteria of being strictly less than will not be satisfied. So they are not actually dominating each other, so you don't have a relation over here. So P is not less than Q. So it will go to the next case. If is Q less than P, like since both the solutions are equal, then even this particular case will not be satisfied. So none of them gets updated, either SP or NP, none of them will get updated. When we go to the next case, so in this particular scenario, we don't have any relation. So if you want to compare 1 and 2, let's see these two, this particular case. So out of these, your P is 1, your Q is 2, F1P and F1Q, and you have F2P and F2Q. So when you compare this F1P and F1Q, it stands out like F1Q is actually less than F1P, and in the second case, in case of F2, the value of P is actually less than F2Q. So you can see like the first criteria itself is not satisfied, like actually in one of these objective functions P is better than Q. So you can say like they are set of non-dominated solutions. So this particular criteria is not satisfied. Like P less than Q is not satisfied. So it will go to the LC. Even this is not satisfied. So it will just be, it will just iterate to the next step. Now let's consider 1 and 3. 1 versus 3, it will also be similar to this. So or maybe we can take 2 versus 3. So if you consider these particular pair with 2 versus 3, F1 of 2 is actually less than F1 of 3, and F2 of 2 is also less than F2 of 3. So it is actually, say if the first criteria and second criteria both are getting satisfied, so 2 is actually dominating 3. So what happens when 2 is actually dominating 3? So if this is my value of P and this is my value of Q, if P is dominating Q, then what we do is essentially add that Q to the value of SP. So this is my SP of 1. SP of 1 is essentially 5. So when you go to SP of 2, you essentially add the value of Q there. So here it will be 3. So then you keep on doing this continuously till you kind of populate the entire values of S and you get all the values of N. Once you get all these values, if NP equal to 0, so like you can think of it in a simple way. If you recollect the graphical way we were solving, you have one solution, say P and Q. In this particular case, if both are minimization problems, here P is actually dominating the Q. So SP is getting updated only when P is dominating Q. And so what you are essentially adding to the value of SP is the value of Q. So if you can kind of think of this in two regions, one is this particular region and the other one corresponds to this particular region. Now Q can be in either of these regions. If this is P, if you see the if conditions here, P should be less than Q, happens to be this particular case when P is actually dominating Q. There could be other case where Q is less than P, which will correspond to this particular scenario. So if you kind of see, the yellow region is where P is dominating Q and the other region is where Q is dominating P. So if Q is dominating P, in this particular region you are updating the value of NP, and if it belongs to this particular region you are updating the values of SP. So what earlier when we discussed, like originally the method has a complexity of mn cube. So in that case we are kind of taking one solution, comparing it with all the solutions to identify which of them are rank 1, and again do it to obtain in this like we delete all the ones having the rank 1, and then we go from the remaining solutions, we again identify the solutions having rank 1, like we keep on repeating it, so it is having an order of mn cube. Now instead of repeating it every time, we are storing the individuals which are actually getting dominated by a given individual in SP. So by storing this, we will utilize them in the next stage to actually determine the rank of individuals. So if you happen to see, once you populate both the values of SP and NP, the next step is you compare whether the value of NP is equal to 0. If NP equal to 0, if NP is essentially corresponds to this region. If this is equal to 0, which means there is no solution which is actually dominating the given value of P, then the rank of this particular individual P equals to 1. Then you kind of add it to your F1. F1 is your front rank. It is a Pareto front which is having rank 1. So once you get the entire all the individuals in the first front, then you go to the next stage. In the next stage, what we do is we take each front by front. So in the first front, the first step is essentially checking if Fi is not equal to 5. Since the first front has some solutions, this will get satisfied, and we are defining Q equal to 5 null set. After that, we'll iterate element by element in the first front, and then for each of them, there is an SP associated with each element. Like here, if you recollect, like here we have for S2 equal to, there is an element called 3. This element over here is a 3 for the S2 value. So this second loop is essentially for that. So for each element, we take and decrease its index by 1, like NQ will be less than or equal to 1. And if in that particular case, if NQ equal to 0, which means there is no solution that is actually dominating Q, then its rank will be second rank. Because we are on the front one, and from front one we are seeing, like once we obtain all the solutions on front one, and from here we are updating the values of whatever solutions are there on the neighboring fronts, on the other fronts. So you are on front one, and when you are seeing a solution here, and if this happens to have an n value of 0, which means this belongs to front 2, and in this particular scenario this will have n value of 1, this will have an n value of 2. So we keep iterating with this till all the values of whatever remaining on the last front has an NQ of 0. Once you get this, essentially means like you kind of have each individual solutions having all the values of fronts. Once all the fronts are determined, the next step is essentially to get the diversity of these solutions. This is the crowded distance diversity, is basically your Euclidean distance, slightly modified form of it. Say you have a front and say you have 3 solutions. If these are your solutions, the first step is you all of them should belong to the same friend. Like you will be considering only the solutions belonging to the same friend. Say all of them belong to the friend 1. Basically, all of them have rank 1. You define a matrix D with D1 equal to 0. Initially, you declare all of them to be 0. Next, you consider 2 different cases. Here we have 2 objective functions. So, one considering f1 and another considering f2. What you do in f1 is first you sort these elements based on the values of their functions. So, if you happen to see in our particular case, f1 is getting minimized in this direction and f2 is getting minimized in this direction. So, when you want to sort the elements only for f1, ignoring the fact that f2 is existing, then your solutions will be like f13 is less than f12 is less than f11. So now you have the next step is essentially like the boundary elements. You kind of set the distances to infinite. The boundary elements here are d3 and d1. You set both of them to be infinite. Now you are left with only one element d2. So how you calculate d2 is essentially d2 plus. You take the objective function values of the other 2 solutions, the remaining 2, the neighboring solutions. So for the second one, the neighboring solutions are 3 and 1. So you take a difference between 3 and 1 by whatever is the entire range of that particular objective function. Like I'm just denoting delta here to say what is the range of that objective function. Instead of 3, if you are having 4 solutions, so you have some solution here, some solution here, the neighboring points for each one of them will be like, this will be I plus 1, or maybe in our case, this is I minus 1 and this is I plus 1. You kind of iterate using this formula. For each objective function, you'll get I plus 1 and I minus 1. You get the difference and then scale it with respect to the total value of objective function and add it to the distance. The same approach you will follow for the f2 also, but keep in mind that this d will be the, like when you are updating, you need to add the values to the d and do not take the value of di equal to, like say suppose you get some value of d2 here. In the second case, you update from that d2. Once you get the distances, now our selection operator should essentially take into a case of that the entire like it should have information about the rank and then it also should have information about the diversity. So when you're doing your tournament selection operator, what we do is first when you have 2 solutions, say I and j, you check the rank of I and rank of j. If rank of I is less than rank of j, then you essentially select the ith solution. If it so happens that rank of I is greater than rank of j, then you select the jth solution. If both of them are equal, then you consider this distance. Then you measure the crowded distance for di and dj, and then whichever is the greater one, like if di is greater than dj, then you select the ith solution. Like your aim is to essentially select the individuals having lower rank and higher diversity. All the remaining operators will remain the same. When you like your essentially crossover mutation will not depend on your fitness value, so they will remain the same. And the next step will involve your survivor. There, yeah.
If we have to select lower rank
Yes.
and higher d value,
Yes.
suppose the rank is same,
Yes.
then this more value of d is sufficient condition.
Yeah. Only if rank is same, you will check the diversity. Whichever is greater, you will take that one. If both of them are equal, then you choose anyone randomly, like with 50% probability.
Another thing, this first we have to take calculated d value with respect to f1, and then while calculating with respect to f2, then that D value corresponding to F1 will be added.
In your sense, F1 is basically your objective function, right? Not the front one.
No, we are taking with respect to F1 and F2. First
Yeah, your
F1 and
objective
then F2.
functions. F1 and F2 are your
Yeah.
objective functions. Yes.
Yes. Okay. Can we
Yes.
take reverse one? Then still it will give the same result.
Reverse in the sense, like you will
First
consider
I
first
take
F2 and then F1. Yeah, it will be
F2.
same.
Yeah.
Yeah, it will be same,
It
right?
will be
Like
same.
both are independent. It will be same. Like you just have to take contributions from all the objective functions and add all of them.
Because this D value coming from the F1
Mhm.
is added in where we are calculating D value
In
with
F2.
respect to F2. Yeah.
Yes. So
So if we
whichever way
take
you do, it will be the same.
so if I do F2 first and
Yeah.
then F1,
Yeah.
result will be same.
Yeah, result will be same. Like you can see from the expression, like when you are doing for that particular objective function, only that particular objective function term is this. So
Okay.
it's just like you are summing over different objective functions. That's it. Just a combination of all of them, linear
Yeah.
combination.
Okay.
I thought of actually showing the code for that. Maybe we'll go through the code once. Not aware. Like, are you aware of Colab? I mean, Python or something?
No, sir.
Okay, then maybe we'll just go through the implementation. Like, forget about what these import statements, all of them are. But we will see just an implementation to see whether how the algorithm convergence and like you have asked previously, how various parameters will affect your solution, right? How to actually check them when you actually code it.
Yeah. Yeah.
I'll share this notebook with you, like after the session.
Mm-hmm.
You can try
Okay.
out. I'll just say where to tweak the parameters, then maybe you can try that out.
Okay. This code is in which language?
This is in Python. You can actually
Python.
use any language of your choice. I've just used Python, like it will be kind of easy for to start with. Like previously we were discussing on Excel, but I thought like in Python, like we'll be actually using Python or some other language, so I thought it would be better in Python.
Okay.
So like the first lines are basically your import statements are essentially these are various libraries which someone has already developed and we are just using them. Nothing more than that. This fourth one is where you are defining your functions. Like we have f1 and f2. F1 I am returning like I have written as return minus x, which means f1 is equivalent to minus x.
Mm-hmm.
And the next function is f2. I'm like in our case it is x square plus y square. The function here is np dot power is essentially doing the power. Like it's similar to the Excel your power method x comma 2 and y comma 2. So like you are summing both of them. So this will be equivalent to x square plus y square.
Mm-hmm.
And here I am defining my parameters. Say I am giving a population size value of 8, n equal to 8, and I am saying the maximum number of generations are 100.
Mm-hmm.
The next step is essentially once you do that, is you need to initialize your population. We are like our values of x and y are both ranging from 0, comma 1. So this rand function will essentially give you a random number between 0 to 1. And inside I am writing n will give you n random numbers like np dot random dot rand of n will give you n random numbers between 0 to 1. So I am doing that once for x and one for y. Once I get the value of x and y, the next step is to actually evaluate the function values. So I just call the function f1 of x comma y to give me the values of all the function values for x comma y that I am storing in a variable f1 val. Similarly for f2 I will be storing in another variable. This function is just to plot you like these are the solutions I got. This is your objective space, and like here this 0 1 these numbers are basically your indices. Like this is the 0th individual. Like all, your individuals are kind of spread. It's like you can see here like when I'm initially initializing my population, I'm taking them from a uniform distribution. So if I were to plot the search space, they would be uniform. But in my objective space, they would be spanning an entire different region because after applying the function, their distribution will change. So these are my initial solutions. So this is the function which will kind of tell whether like if you have two, so like we were discussing about P and Q, whether P is dominating Q or not. I've just defined a small function, A is dominating B or not. So when you want to say whether A is dominating B or not, what we have to do is two things. So like here, there are essentially two things we need to check. For all values of objective functions, for each and every individual, one should be less than or equal to the second one, and there should be at least one function where it is strictly less than the other. So I've kind of written the same conditions here, slightly rearranged it. Like instead of saying less than or equal to, I put a condition saying it is greater than b of I. If it so happens that if a of I is greater than b for any one of the solution, then actually a is not dominating b. Here, like in the original case, we told a of I should be less than b of I for at least one of the individual. I am putting that in a reverse way, saying if at least one of the case, if a is greater than b, in that particular case, a is not actually dominating b in the case of a minimization problem. So that is the condition I have kept in this particular line. And this is the next case where I am saying like this for loop is basically will kind of go from one solution to the next solution, as your n is essentially your total number of objective functions. Say if m is your number of objective functions, so you are going from one objective function to another objective function and checking the value of whether a of that a is essentially your p is actually less than or equal to second one. If that is the case, then a is actually dominating b. This function is clear, right? Any doubts in this?
Just explain again, sir.
Yeah.
A is P and B is Q, right?
Yeah. A is P and B is Q. Or maybe I'll just write
So
P and Q.
here we have to take both X. It is a its parameter should be X and Y, na?
X and Y in the sense, no, we are only, while you are comparing whether one is dominating the other or not, you are essentially dealing with only their function, objective function values. You don't have to worry about their actual values, right?
Okay.
So now I hope it is clear. So like P, if it is one of the objective, if P is greater than Q, then P actually not doesn't dominate Q. And for all the objective functions, P should be less than or equal to Q. PA should be less than or equal to QI.
Yeah.
So this is one function. This we have seen this is the algorithm for NSEA. So we'll see that. So like in that case, first we define a value of S to be phi. Phi is your empty set, and then you have S. N will be kind of like, if you recollect, S will correspond to the yellow region, and NP will correspond to this lower region. SP will tell you like it is similar to the dominance, the rank method. Basically, it will tell you what are the solutions that are actually being dominated by the current solution, and NP will tell you how many solutions are actually dominating the given solution. So initially, you define all of them to be empty, and here for rank, I'm using like instead of 1, we are actually using 0. The index is a little bit changed because the index will start from 0, so I'm just using 0. 0 indicates rank 1, 1 indicates rank 2, so you have to essentially increase the value by 1 to get the actual rank. So it's the same algorithm. So for each P, so what to maybe I'll put both of them side by side. So if you see the algorithm, the first step is essentially for each P belongs to capital P. So instead of that, here we are writing it in a for loop for small p in the range of n. So basically n will be your population size. Like this P is your parent population. So here instead of P, we are just writing in this particular format. So what happens is P will be each and every individual. The next step is SP equal to phi. SP equal to phi is your null set. So this is the format we are using in Python. In Python, you just write SP is equal to a blank. Like you just keep a braces, it's an empty list. Doesn't have anything. The next thing is NP equal to 0. It's the same thing I have defined over here. And again, there comes another loop for the values of Q. So it will be like for Q, which is in the range of N. What we do is compare P with Q. If actually P is dominating Q, so I'm writing in this particular way. If A is dominating B, I've written P comma Q. Then what you do, you essentially add that particular value of Q to P. So adding like union is actually your append function here. So I am adding Q to SP. And then this is a second
This
case.
A dominates
A dominates B is
is
the
a
function.
function.
Yeah, is a function which we define here. This is a function we discussed previously. A dominates B of P comma Q will tell you whether if P is dominating Q or not. That's it. Here.
Yeah.
So if A dominates B, first I give the parameters as P comma Q. Then if it so happens, then it's as per our algorithm, you should append the value of, like, you should take a union of SP and Q. So that is this append statement. If it so happens Q is dominating P, like I use the same function, but instead of P comma Q, I will be passing Q comma P. That's it. That's the only difference. Then what I have to do is increment the value of NP. So that is NP equal to NP plus 1. After doing this, I'll check if, and after iterating over all the elements, all the individuals in the population, I'll check if my NP still is equal to 0 or not. So like here, that is the if condition in this particular line. If NP equal to 0, what I have to do is the rank of that particular P, that particular individual is, in this algorithm we are having 1. So instead of 1, I am saying 0. Like I am defining rank from 0 instead of 1. So I'm just keeping a value of 0 here. The next step is essentially union of f1 and p. So I'll just use the append statement here again. So like it will be f of 0 dot append of p. So I'm adding p to f0. This is the stage 1 process.
I hope in the exam there is this. I need not to code.
No, there is no coding.
Okay, sir.
I was just showing this code so that you asked how parameters will affect, right? So that I can show you some
Yeah,
of the simulations. If you go through
yeah,
the
yeah.
lecture, you have some simulations. So I thought,
Can you share,
yeah, I will share this
sir?
code. I'll like in your there is a last call recorded lectures, right? Live session. There will be in the tab in your NPTEL portal. There will be a live session. Some one tab will be there at the bottom. If you click on that, it will direct you to one Google Sheet.
Okay,
In that Google Sheet, you can see some one link for presentations. If you go through that,
ah,
you can access all of this. I'll
okay,
share
sir.
the notes as well as this particular collab
Sir,
notebook.
sir, do you have see Python is? I am new to Python because I don't know Python.
Okay.
So, uh, if you have in MATLAB or mm, Excel,
Excel will be kind of difficult because you need to have this, like unless you have VBA, you will not be able to implement it easily.
okay, okay.
MATLAB is fine, but it is not open source, so that's why I have not used MATLAB.
Uh-huh. But there is a no, Octave type,
Yeah,
Octave or
Octave is there
something.
still. Octave is there,
Uh-huh.
yeah, but I don't have Octave. Fine. I I just have the notes in this Python.
Okay, sir. Yes,
Yeah, but it will be similar.
reading.
Like the algorithm will be similar.
Yeah,
Like
yeah,
if you
algorithm will
see
be
the
similar.
algorithm versus this one, it will be more or less reading
Ah,
the same.
means I have to translate it.
Yeah, that's a bit of thing.
Ah, okay, sir.
That's fine. So if you were to see for the stage 2, here we started with I equal to 1. So this is because our index is ranging from 1, but in this particular case, we are actually using I equal to 0 because we have kind of defined the rank from 0. So the next step is you check whether that particular value of front is equal to 5. Phi is null set. If you are having a null set, basically the number of elements in that particular set is equal to 0. So I've defined this len is basically will give you the length of that particular array or matrix, whatever is there. Here f of 5 will give you that particular matrix, and you are saying the length of that is not equal to 0. Then you define q, which is equal to a null, initially a null set, and then you kind of iterate over. The next step is actually iterating over the f5 for that particular friend. So that is this particular statement. For p in f of I, will kind of take each and every individual from the first friend. The next is essentially for each q in S belongs to SP. That is the same statement here. For q in S of P, you decrement the value of NQ, and then if NQ equal to 0, then the rank of that particular thing, that particular individual will be increased by 1, and then you add that to your queue, and you keep on iterating this. Once you are done with your entire population in that particular friend, then you increment the value of 5. That is, you are essentially going to the next friend. Once you go to the next friend, like you have all your solutions are actually in your queue. So you append this queue, like you add this to your f of I. So your I will be initially I is 0. So that is your first friend. Now once you have all your solutions in queue, then you are keeping them in your next friend. So f of 1, or essentially your second friend, will be queue. So once stage 1 and stage 2 are complete.
So here this dominance depth, this is nothing but finding d values.
Finding not d values. D values is your distance. Dominance depth is essentially finding your rank.
Okay.
But like in addition to finding your rank, like if you are aware of the breadth first search in graphs, you are aware of graph theory. Oh, fine, leave that. So basically, what we are saying in dominance depth is like you take a locus of all rank 1, and then take
Yeah.
locus of all rank 2, take locus of all
Hmm.
rank 3. That is what is this.
Yes.
So in these solutions, if you see the output is something like this. The first line is your friends. So zeroth friend is essentially having individuals 2, 3, 5, and 6. The first friend is having individuals 1, 0, 7, and 4. The next friend is empty,
Hmm.
basically doesn't have anything. So all your 8 solutions are essentially split into 2 friends. The first one and the second one, that's it. This is just a plot of it. So these are our individuals. What happened? One second.
So suppose there are eight solutions, and if we uh, uh, in- if I get F1 and F2, then we can say the remaining are in F3. Or the last front will always have one only.
Last friend can have 2 solutions also, right? It can have 2, 3, any number of solutions, right? You cannot say how many solutions you'll be having in the last friend. So you can take in this particular case, like this is the friends you are having. Here there are 2 friends. First friend has 3 solutions, and second friend is having like, first friend has 4 solutions, and second friend is having 4 solutions. So your last friend is your second one, and that has 4 solutions.
No, in the one of example, uh, F1 was having some three solution,
Okay.
and front two was having some four solution. Then last one, only one was left. So can we conclude that it will be in F3? I need not to calculate.
Okay, so you are saying you have only 8 solutions. Out of them,
Eight
4 of them
solutions,
are in
yeah.
front one, 3 of them are in front two.
Ha,
So the last one will
yeah.
be in front three. That's what you are saying.
Ha, can without calculation I can go that
Yeah,
it will it
if
is
you are
in
sure
front
that
three.
only one is left and that is not belonging to either of this or this, then that will be in the last friend.
No, because out of eight solution, I have already checked
7
seven.
solutions, then for the last one you don't have to do. Yeah. If it is only one solution.
Oh,
But usually
okay.
it might be like here you are left with 2 solutions, then you cannot say that, right?
Yeah.
Then it
Mm-hmm.
can be like 1 1, or
Yeah, one. Yes, yes.
can be 2 0. There are other
If one is
possibilities.
left, we can say that it
Yeah,
is
if one
in
is
the
left, then
last
you can
one.
say it is in the last friend. So once we define the rank, the next step is your distance. You need to update the crowded distance. That is essentially this. Maybe I'll just take the same. This will be the similar. Like initially you define all the values of di to be 0. That is your first step here. All values of di should be equal to 0. That is similar to this one, this particular line. Di equal to 0. Next, you'll here we have only 2 objective functions. So instead of writing a loop, I've just considered 2 different statements. So for the first objective function, what we are saying, first thing is you need to sort the values on a given friend. So the parameters, if you see for this particular function, are like you are taking the whatever your population is, that is, this is my x and y, and f1 value and f2 value are the objective function values for the given values of x and y, and fy is that particular front, whatever front we need to calculate this distance. Like distance is calculated only for the solutions on a given front. So this sorted function will just sort all these values.
So sorting means finding the distance. From here it has come. Ascending order, we are ascending order of the D, we are sorting. That is why it is sorting.
Sorting in the sense,
The name has come from this only.
no, that is a predefined function that will sort the values. That is a predefined function in Python to actually sort the values of this.
No, in this NSGA, S stands for sorting.
Yeah,
The sorting is mainly for finding the
dominance.
means,
Dominance.
dominance, no?
Yeah,
In ascending order.
yeah.
The D value we are taking in ascending order, right? That
No,
is
no,
called
not the D
sorting.
value. The rank. Rank we are taking the
Right?
ascending order. D is your distance, which will be in the descending order. D has to be higher. Rank has to be lower.
D should be higher, yes.
Yeah, T should be higher. So you like once you get the entire population, what you do is first sort them based on rank. Next, you sort them based on your dominance. Like first you do an ascending order based on rank, and then after you obtain within each rank, you do a descending sorting based on your distance. Once you do both of them, then you get your entire solutions. From there, you pick the values.
So,
That
so
will be
sorting.
your survivor step. We'll come to that.
Right. So this sorting has come from this process.
Yeah,
When we
once.
say a non-dominated sorting.
Yeah. So here for objective one, once we sort all of this, then we kind of, for the first and the last one, those are essentially the boundaries. So they will have infinite distance. Like distance is essentially, we kind of say I plus 1 and I minus 1. So like the boundaries doesn't have either, like if you're at the left boundary, you do not have I minus 1. If you're at the other boundary, you won't have it having I plus 1. So I'm setting both of them to be infinite. Except for the boundaries, for every other solution, what you do is for that particular individual, you are updating the distance value. So d of that particular individual, the sorted one fs of I equal to, you update the value for the first like here is for objective 1. So I plus 1 solution, like it has two neighbors I plus 1 and I minus 1. So you take a difference of I plus 1 minus I minus 1, that will give you 1 length. You kind of normalize this distance with respect to the maximum value minus minimum value. Like when you sort your entire, like fs contains your sorted values. So fs of 0 will be your minimum value, and fs of minus 1 in Python essentially means the last value. Like, so the last value when you sort them will be your maximum value. So you are normalizing with respect to maximum minus the entire range of your particular objective function value. You do the same for both the objective functions. Like this entire code is essentially for that. Once you do both of them, then whatever is the value of your distance will be returned by this function. The next step is your tournament selection. So when in tournament selection, it will be similar to what we are doing in our normal GA. So you pick two solutions at random, like without replacement. Once you get both the solutions, you compare one solution with the other. Which one of them is better will be going to the next generation. The one which again you kind of repeat it continuously till you get the number of individuals which are equal to your original population. So first step I am doing here is you are generating the random numbers. So what I am doing is you just generate, say in our case n is equal to 8, like your population size is 8. So you just select the 8 random variables, like you generate 8 random numbers from 1 to 8 without replacement. The replace equal to false will give you without replacement. And this counter is essentially to count the number of individuals that you are adding to your population. So it should be less than n, like your population size. So I am taking two individuals to compare. So one is at the current value, one is the next value. Once I get a random numbers, I am just picking two of them and comparing whether the rank of the first individual is less than the rank of second individual. Like our objective is essentially to select the individuals having lower rank. So if the first condition is satisfied, OP is my output. The output should have P1. If rank of P2 is less than rank of P1, then the output should be having P2. If none of the above two conditions are satisfied, which essentially is like equivalent to saying rank of P1 and rank of P2 are equal. If both of them are equal, then we will go to the distance. So if both of them are equal, then I will pick that particular friend. So f of rank of P1, say if rank of P1 is 0 and rank of P2 will also be 0, they are equal. Say fi will correspond to first rank. So in that particular case, I will calculate the distance for the individuals on that particular friend, and I'll compare the distances. If dp1 is less than dp2, which means I have to select the p2 individual, otherwise I'll be selecting p1. Otherwise, in the sense, if p2 is actually less than p1, then I'll be selecting p1. If again it so happens like even distances are also equal, like if ranks and distances both are equal, then I'll come to the last case. In that particular case, we need to choose any one of these individuals randomly. So I will generate again a random number. If that random number is less than 0.5, then I will choose P1. Otherwise, I will choose P2. This is equivalent to saying I am choosing any one of them randomly with 50% probability.
Sorry, here,
Yeah.
suppose rank of P1
Hmm.
is greater than P2,
Yes. This
but
particular case.
distance is less.
But
Yeah, but distance is less. Distance is less.
yeah. So
Then which one to be selected?
no. If you remember, we will calculate distances only on the same rank.
Only for the same rank.
I mean, you are calculating distances. If you remember, we are calculating distances only for the individuals on the same front. If you have individuals on rank 1 and rank 2, the distances are different, right? For
Yeah, yeah.
rank 2
Okay.
individuals, distances are calculated with respect to rank 2 friend. It has nothing to do with rank 1 friend.
Mm-hmm.
But as you said, like this is what we will come to the next approach. Like NSCA is one algorithm. There is another algorithm which is strength Pareto. Like that will be the next lecture. Like I think
Okay.
it's already uploaded on the videos, the week 8
Yeah.
lectures. In that particular case, you will consider it in that ways. Like you will consider distance as well as this different friends and add all of them to get your fitness. That is another approach.
Mhm.
But in this particular
So
genetic
here we have
algorithm,
to find
here we are only considered for that particular friend. We are not worried about other friends. If you are having something on friend one, that is definitely better than friend two. Only if you are having two solutions on front one that you need to compare, only then you will think about measuring the distance between them, and you will select the one which is having greater distance.
okay. So first we are means sorting based on rank, and
Yes.
then to get the front. Suppose front one there are four solutions,
Hmm.
and then we are selecting based on the distance out
Yeah,
of this
and like
four
in
solutions.
tournament selection, you just pick two individuals from the entire population. So you cannot say beforehand that the two individuals will be of rank one or rank two, right? So when you are
Yeah, yeah.
comparing two individuals, if both of them belong to rank one, then you will measure
Hmm.
the distance. If say one is rank one and rank two, then definitely you will select rank one. There is no point in selecting rank two. Like if you keep on doing that,
Suppose from the rank P1 rank is greater than P2,
yeah, then you
then
select the
still we
P2.
P2.
Yeah,
Okay.
that's the statement. If rank of P1 is greater than rank of P2, then you select P2.
P2. Then no need to calculate a distance.
No need to calculate the distance. Yes. Like the distance doesn't have
Okay.
a meaning in the way we define. We define only
Yeah,
for the same rank.
yeah, yeah.
Okay.
ठीक है.
So if you've seen here, like once you do the tournament selection, like even in our genetic algorithm, only one round will give you four individuals. Like each time you are taking two individuals and giving one output. So when you are having eight individuals and you are taking without replacement, you will generate four pairs, and your output are only four individuals, but we need a population size of eight. So we need to kind of
Hmm.
perform it twice to get all the population. So I've just done it twice. So the first one, I've started with an empty set. If you see the last one here, that I've just picked an empty basis. Just say that there are no solutions initially. Once I perform that, OP will have four individuals. So for the second time I'm performing, I will pass the four individuals also. So the final output will have eight individuals. So just this is just a plot in the objective space. So the dots are essentially your normal solutions, and the stars are basically the ones selected after a tournament selection. So all the ones that are selected belong to the first rank.
That blue one.
Blue ones are basically the ones that are not selected.
Okay.
The next are your crossover and mutation operators. Here we are using a simulated binary crossover operator. You can select
Sir,
yeah.
sir, you have taken, you have selected four, that is star one, red star,
Yeah.
and then but you have to keep the eight numbers.
Yeah, I will
So
do it
remaining,
when
how
in
will
your
you?
final loop you will actually do it twice.
Uh, so
We will come to the final algorithm. Like I'll combine all this in one small place, then we will see what happens actually.
mhm.
After your tournament selection, the next step is your variation, that is your crossover and mutation. For the crossover, I'm using the simulated binary crossover operator. So in that particular, the first one is the parameter there is your eta c, if you color. That will determine how much spread you need to have in your solutions after your crossover. So the first function is beta crossover will give you the value of beta, that is a random number. So the next is your crossover operator, like it again is depending on your beta value. There are two possible, like you taking two individuals x1 and x2 and given a value of eta c. First step is you
So
generate
this crossover in SGA2 is similar to
the
RGA.
previous RGA. Yeah,
Okay.
but you can actually use anything like okay, the name will be different, but you can use your own crossover operator. Like you can use any crossover operator of your choice.
Mhm.
They have the others have used simulated binary crossover.
Okay.
Once you define b1 and b2, you get the new values of x1 and x2 using the same formulas. But if you recollect, like there we have seen like if you have two individuals, your solutions within some limits x2 and xl and xu, like lower and upper limits. After crossover, like you are essentially having some probability distribution, and it can so happen that the new individuals you are getting will exceed the bounds. So there we discuss like if something like this happens, you need to cut it off to the value of the bounds. So the new solution, whatever is getting, if it exceeds the values of the bound, then you make it equal to the bound. That is exactly this particular step. So the new solution, the one you are getting, is actually greater than 1. Our limit is 0 to 1. So if it is greater than 1, then you are making it equal to 1. And if it is less than 0, even then it is less than the lower limit. So you are making it equal to 0. Same for the second solution as well. This is for the crossover operator. Now you need to do this for the entire population. And but this is not done always. This will be done only
How much error will occur because of this forcefully we are limiting the x value
uh,
to
why
lower
were
and
you
upper
calling it
bound?
an error?
It may affect the result.
But your result, if it is, if you are not doing this trimming, then what is happening is you are getting solutions which are not actually satisfying your criteria, right? You have put a bounds for your variable 0 to 1. So if you are
Okay.
not doing this trimming, whatever solution you are getting will have some value which is actually not within that bounds. So that is
So
actually in the infeasible space.
can we change the parameter, the distribution parameter, so that it comes within the bound?
You won't be able to do it because it's a Gaussian distribution. Like it's a kind of a Gaussian distribution that will
Yeah,
become
yeah.
minus infinite to infinite. So you can only reduce the probability, but you can never make it equal to 0.
Okay, fine.
There are approaches here. You can actually change your, this beta function itself you can change.
Beta function. Yes, sir.
If you change the beta function in such a way that it will be bounded, then it works.
Within the bound. Yeah.
Yeah, then it works. But if you are to use the same beta function and change the value of beta c, so that will be a bit tricky. Like you will like even whatever eta you put, however small eta value you put, they can always occur some value which is exceeding the bounds. That's just
Okay.
because the distribution is minus infinite to infinite.
Hmm.
So in the crossover operator, you do not perform crossover always. Like you have certain probability only with which you need to apply the crossover. So what you do, you pick two individuals. So this particular line is actually picking two individuals from your entire population. P is my entire the individuals after tournament selection. From them, so random dot choice will actually pick individuals. So I'm saying from P, you pick two individuals without replacement. So those two individuals will be P1 and P2. Next, I'll generate one random number. If that particular random number is less than or equal to PC, PC is my crossover probability.
Yeah.
Only then I'll perform the crossover. So crossover operator will perform on X, like basically I'm performing it twice. Basically I need to do it both for X and Y. I have two variables here. So I'm doing it independently. So like for the first X1 will be stored in O1 and O2. I'm appending them to the off is essentially your offspring X and offspring Y. If it is greater than, if the particular random number is greater than PC, which means you should not perform crossover, so I will just use the same variables. Like of X will have X and of Y will have Y. And return the values of this. So this particular operator, OP will have after your tournament selection, X and Y are your original individuals. When I pass to them, of X and of Y will have the solutions after the crossover operation. So after crossover operation, I need to pass this to the mutation. Mutation operator will also, I'm using the polynomial mutation operator. It will also have similar form for your beta mutation operator. And the operator will have one parameter called delta I. Will collect delta I, then you take a value of X and you add the delta I to the particular value of X. So in mutation operator, what you do is you generate one random number delta I from the same distribution, like similar to the beta, and from this delta I, to get a new individual, you are taking the current individual, you are adding delta I times your range. This is the kind of mutation I am using here. Same thing is applied, like first I will generate a random number. This beta mutation will give you one random number from beta distribution. The next is xn is your new value of x, that is the current value of x plus di plus random number into xu minus xn. In our particular case, x ranges from 0, 1, so that range is 1, so I am not writing coefficient here. Again, it can be possible that your value of x after mutation is exceeding the bounds, so you just do the same. If it is actually exceeding 1, you make it equal to 1, less than 0, you make it equal to 0, then you return this value. So this mutation function here actually performs the mutation. So first you define, you get one random variable, check if that random number is less than or equal to the mutation probability, only then you perform the mutation. Like only then you apply the mutation operator, otherwise you just append the same values of x and y. After crossover and mutation, the next step is actually to do the survivor or elimination, is basically to select the individuals that are good to go for the next generation. So how do we do that? Is so I have of x and of y are basically my offsprings. So of f1 val will give me the objective function f1 value for the offsprings. So first line will give you the values for f1, second line will give you for f2. Now
What is the of x and of y?
Of x are basically offsprings x and y.
Offspring, okay.
Yeah, offsprings after your crossover and mutation operator.
Okay.
So you combine both the population. The combine is essentially your concatenate. You will join both the parent solutions as well as your children of offsprings. Once you
So it
combine,
will be
yeah,
two n members now.
yeah. Now you are having 2n members. Once you get the 2n numbers, then you do the dominance depth for all the 2n population. Like dominance depth, you are performing for new function values. Now you are giving a value of 2 into n. Basically, you are having 2n population. Now you get rank of all the individuals. So this is the rank of the new individuals. So now you will be having 16 solutions here.
Yeah.
So for these 16 solutions, now it has essentially split into 3 fronts. So 2, 3, 5, 8, 9, 12, 13, 14 are belonging to the first front. 0, 7, 11, 6, like the next 4 solutions or 5 solutions will be in the next front. The last 2 solutions will be in the third front. So this survivor function, what it essentially does, it takes the new offsprings, their objective functions. Then the first step is you take rank by rank. Like for the like we discussed previously, how you choose is out of all your parent plus offspring solutions. First, you sort them based on rank. Next, within the same rank, you sort them based on your distance, crowded distance. That is what we are trying to do here. So first you define rank equal to 0. Then what you do for that first rank, you calculate the distance for each individual and then sort them. This sorted function here, there is a reverse. Reverse equal to true will essentially do the sorting in the descending order. So once you get the descending order, you select one by one and add them to your final. F1 is your final solutions. You keep on doing till this condition is satisfied. If len of Fn, yeah.
So descending uh, for the same rank,
Yes.
you will prefer more D, no?
Yes, that's why we are sorting in descending order for the same rank. So
Okay,
first
descending.
I
So
fix the
highest
rank.
you will take. Huh?
Yeah, first is I'm starting with rank 0. In the rank
Yes.
0, within the rank 0, I'm sorting based on distance and then selecting from the top, like whatever comes first.
Rank 0 means basically it is 1. Huh?
Yeah, 0 is basically 1. Yeah.
Hmm. Okay, sir.
Okay. Now I'll keep on adding these values till I get a population size of n. That is this
Hmm.
particular condition. If that particular thing happens, then you just return it. You stop getting the population and you just return these values. That will be your survivor. So these are the values after applying the survivor operator. So if you can see here, out of these individuals, we got 9, 13, 12. Like if you see 1 and 10 basically have rank 2, or just see the rank 1. If the second index is 0, then it is rank 1. There are 8 individuals with rank 1, and that is
Yes,
equal
yes.
to our population size. All these 8 individuals will essentially come after your survivor operator.
Yeah.
The next step is like after you get your survivor or elimination step, the next step is to actually get them into the next generation. So what I'm doing is you go through each individual and assign the value of the new variable to the previous variable. So x of I is my previous variable, xn is my new variable. So what I'm saying, you just take the xn value and add it to x and make it equal to assign that value to xi. Same for ya and the function values. And then what we have to do is repeat this continuously till our criteria is satisfied. That we'll be doing. So this is essentially some helper functions will do that. So this is our overall algorithm in one place. So if you can recollect, like I'm defining the population size to be 8, total number of generations to be 100. Initially t is my counter, like the algorithm is similar to our general algorithm. Small t is my counter, which will range from 0 to t. The next step is initializing my population. I'm using a uniform distribution to initialize my population and then calculate the function value. The next is iteration till convergence, that is this while loop. While t is actually less than my capital T is the maximum number of generations. Set axis is basically to just show you some visualization, you will see that later. So you can leave that for now. After your the first step inside your while loop is actually to do the tournament selection. To perform tournament selection, we need to know the dominance depth of, like basically we need to get all the friends rank wise. So first we do the use the function dominance depth to get the dominance depth and rank of every individual in the population. Next we will perform tournament selection twice. Like each tournament with selection once will give you 4 individuals. So I'm doing it twice to get all the 8 individuals. After selection, next step is your variation. Here you can see like I'm using these particular parameters eta c to be 15 and eta m equal to 10. I'll do the crossover and mutation operator. After crossover and mutation operator, we will again evaluate for these offsprings. I'll get the function values. Once I am done with that, the next is actually doing the survivor stage. For the survivor stage, I need to concatenate both the parent as well as offspring population. So that is this, the concatenate step. Then evaluate for these new individuals, and then again apply the dominance rank and then apply the survivor, which will give me the final individuals that will go to the next generation. Then I will actually assign them to the next generation and then plot these.
So in this program, where it gets double, population size becomes 2n.
Population size becomes 2 and is here. If you can see this,
Where
yeah, you can see the cursor, right?
cursor, yeah, combine the parent and offspring
Yeah.
population.
Yes. So you are using that concatenate function, right? That is actually
Means
adding x and offspring of x after your
after crossover
crossover
and
and mutation.
mutation.
Yeah.
Okay. So you are after crossover and mutation, whatever it comes, that you are
Adding to my previous parent
adding to
population.
parent one. Okay.
Yes. So then I get to new values of f functions, and then I will keep on iterating the value of t to get the final solution. So just see one animation. This is a kind of, you can see how solutions are actually changing over time. I don't know if it is visible in the video. Like you can see the solutions are gradual. Like the red lines are basically your bounds for your feasible region, and the blue line is your Pareto friend. On the left side is your objective space. On the right side is your search space. So you can see how the search space variables are gradually changing, so that you will get solutions towards the dominant Pareto friend.
This animation function is there in Python.
Like I'm just plotting it repeatedly after certain time.
Okay, okay, okay.
You can see like around 80 generations or so. Most of the solutions have already reached the Pareto friend.
Yes, yes.
I've kept a maximum generation of 100, so I think it stopped over here. But if you increase the number of generations, then you can see like after a certain number of generations, the solutions won't be changing. Like they'll stuck.
Yes,
Like here you can see like one solution is actually little above the blue line, but if you
yes,
increase
yes.
the number of generations, all of them will lie on the blue line itself. Maybe I can
Mm-hmm.
show you that one. Maybe we can use more number of, like 8 is too small to see that. If you say 32, 32 individuals, and maybe you can increase your generation to say 200, you may be able to see that. Yeah, when you have more individuals, you can see like how fast it converts to the Pareto sign.
Yes.
Once you reach the Pareto round, you can see like solutions are essentially trying to separate from each other. That is essentially because we kept that distance measure. So they will try to move apart from each other.
Mm.
Yeah, like even if you run for 2 more minutes, that's what is going to happen.
Yeah.
Maybe I'll share this so you can try with other parameters. Like you can actually change the value of eta c here.
Mm-hmm.
All these eta c. Oh, sorry, what is happening? Yeah,
Where from I can download the Python, sir?
you can actually run it online. Uh,
Online.
yeah, I will share it. When you click on this, it will be open in something called Colab.
But there should be
You should have a Google
com-
account. That's it. No other license or anything. Nothing is required. You just need to have a Google
it
account.
doesn't need a compiler, sir.
No, it's online. Like it's, you don't have to have anything. Just a browser and one Google account. That's it.
Okay, okay.
You'll be able to run this. So you can change, like you can play with these parameters. Basically, eta c, eta m, and your crossover rate and mutation rate
Yeah, yeah.
probabilities. Like I can show you one if you want now. Say suppose if my mutation rate is 0.5, like I'm increasing
Mm-hmm.
my mutation rate. What we think to like what can happen is essentially if you are putting in mutation value of 5, then these solutions will not converge, might not converge faster. They will actually take more time to converge. You can see that maybe, or maybe this is a simple problem they might actually converge. So, but they will keep on oscillating. See, like you can see the solutions are not directly coming to Pareto front. Even after reaching there, something will go here and there.
Yeah.
It's around zero point 0.5. So every 50 generations or so it will happen. Okay, now it already converged. Convergence is around
Yes.
20 generations or something. In the previous case, it converged around 10 generations or something.
Mm.
You can play with these numbers to get what is happening there.
But sir, I heard that Python takes longer time because there is no compilation sort of thing
Python is actually an interpreter, yeah.
compared to
Yeah, yeah.
C, and
Yeah,
it takes
I've
more
just done
time.
this for a demonstration purpose.
Ah,
When
sir.
you're actually using, you might be using C++ or some other language.
No, I don't know C plus plus.
Okay, maybe MATLAB or whatever language of
Uh,
your choice. This is only for
uh,
demonstration purpose to just
uh.
show you the
Sir,
visualization that it actually
one
works.
more thing.
Yeah.
Suppose F2 is maximum to maximize.
Okay.
So where I can put F2 as a minus F2?
In the first step itself. Here when I am defining the function, right? See, like here I can put the same problem in a different way. I am saying minimize f1. Instead of that, I can write maximize f1.
Okay.
If you like, we define the problem in this particular. One second.
This whole method is just for minimization of F1 and F2. So if F2 in the problem F2 to be maximized, I can write F2 as minus F2.
Yeah, this is our
That will
original
do.
problem, right?
Ah,
I can write the same problem in a different way. You want to maximize f1, which is
ah,
equal to x,
X. Okay.
and minimize f2, which is equal to x square plus y square.
Ah, so
Both
suppose
the problems are
maximize
equivalent, right?
F2, I can simply put minus sign before the function.
Yeah, that will work.
Minus of x square plus y square.
Minus of
So
x
it
square
will,
plus y square. Yes.
then it will maximize F2.
Yes.
Okay, sir.
Maybe if you want, we can try that. Or maybe you can try. I will share that code with you so you can try that.
Sir, which one is better? One is this one by putting the minus sign, and another one is by putting 1 upon f.
1 upon f in the sense. Okay, you are saying if you want to minimize some function f.
Suppose f1,
Okay,
suppose I
okay.
want to minimize, change the yes, is minimization of f1 of minus x. I can, for maximization, I can write 1 upon minus x. Will it be okay?
This is what you are asking, right?
Yeah,
This is easier one to do, right? Minus f.
minus f is easier. Okay.
Easier to do in the sense easier to implement as well. Like the only problem with 1 by f is if you are sure that it won't be having any singularity, then it is fine to go with it. So like it can so happen that in your domain your function will be 0.
Mhm. While solving the problems or whatever you have discussed here for getting the Pareto friend and then getting the distance, so this is for F1 and F2 both minimization.
Yes.
Suppose one is maximization, then
Then you
what
convert
changes
it.
we have to do?
Only change that, put a minus before that in the first step. That's it.
Okay.
Like you just convert the maximization to minimization by putting a minus over it, and you can use the
Minus
same
over
steps
before the
before the function value. Like
function.
whenever you are calculating the function value, put a minus over before it. That's it.
Okay. Okay, sir.
So this is the next algorithm like we were discussing previously. Instead of actually just being dependent on your rank and your distance, like strengths and all that.
One minute, sir.
Yeah,
In the NSGA2,
yeah.
what is the overall complexity, computation complexity in
Uh,
case of NSGA2?
see the main step in that is this particular one.
Hmm.
This is the where your most of the time is basically to compare all of them. But you cannot say just from this because usually what happens is when you are having so many objective functions, you need to actually evaluate each of these functions.
In previous assignment number 7, this was the question.
Okay. The complexity of this NSC algorithm, right?
Yeah, yeah,
Yeah, it
yeah.
was basically talking about this sorting. So with this, if you use this particular algorithm, it will be of this complexity, where m is your
Because
number of objectives and n is your number of like size of your population size.
yeah, because there are means three steps, and each one is having a different computation uh, complexity. So overall means I have to take maximum one. Na?
Yes.
Then it should be
Which of the
means
three
M
steps you
and
are
Q.
referring to?
I think one is where you are populating it. No, no, populating is not the thing. One is your this thing sorting, and there
Yes.
was diversity.
Okay. If you see the
I think
diversity function,
diversity.
we'll
So
go one by one.
diversity will have some log function, no?
No, all these logs and all this we are like basically when you're computing the complexity, we are only worried about the loops at this point. We are assuming that all these logs, whatever are there, are getting kind of done in a very finite amount of time, like basically order of one. Only loops is what we are worried about,
Mm-hmm.
at least at this level. So if you see the crowded diversity function, it essentially has only one loop or two loops maybe. Like basically one is for the objective functions and one is for the this particular values.
Yeah.
So essentially I have only two loops. So this will be order of m square. Or
What will be the
not
order?
m square, it will be something like order of m into whatever the number of individuals here. That will kind of vary. On the worst case, you can take order of mn.
Mn. Okay.
Like that's the worst case.
Yes.
Usually it will be less than that. That's a different issue. But first case is what you will talk about. But the major one, like the limiting step, will be somewhere here, right? This is where you will compare each individual with every other individual in the
Yes.
population.
Yes. Yes.
So this will be the limiting one.
So here it will be uh, Mn square or Mn cube?
Mn square. If you use NSCA,
M,
then it is Mn square. If you are using
okay.
some other sorting technique, then it will be Mn cube. That is the
Some other.
brute force, in the sense we discussed the original case, like use some of this bubble sort or any of these algorithms.
Mm-hmm.
Like we don't worry about, like we are not actually implementing SP, NP or this kind of strategy. We just use some brute force technique. You take one solution, compare it with all the solutions, say whether it is fine or not, get a rank for that. Again, you go to the next individual, compare it with all the solutions, get a rank of it.
Yes.
To get for one individual, it needs to be Mn square. Like that you have to do for n individuals, so it will be Mn cube.
Mm.
Got that? So that will be a brute,
So,
like you won't be implementing that anyway. You will be implementing this particular sorting technique. So it will be Mn square.
so, so it will be Mn square.
Sorry.
Okay, sir.
Okay. Have any other
One
questions?
one option was having some log function. Why it is log function?
Yeah, you can have log functions as well. Something like you are aware of
Like
binary search method. So where your basically your whatever number of the solutions are there will get half each time.
hmm.
So say you are starting with 16. When you keep on doing this binary search, basically from 16 it will get reduced to 8, 4, 2. So it will kind of get reduced exponentially, but not in the power of e, but in the power of 2. So you will have a logarithm to the
Yes.
base 2. But we don't have
Okay.
anything like that here.
Yeah, yeah.
Have anything else to discuss? Because basically I think tomorrow, I mean, the next week session will be the last session,
Yeah.
mostly. If you have any questions, we can close
Hmm.
before going on to whatever is covering in the next session. If you have any other questions, we can discuss now, or maybe if you can come up with something in the next week, we can discuss that.
Okay,
Having
sir.
15 minutes now. Maybe I'll briefly go
In
over
exam, it will be similar. Question will be similar to
your
assignments.
assignments. Yeah,
Whatever we have solved assignment, it will be similar questions.
should be similar. Like I'm not actually aware of the questions. I will get back to you on that.
Means I don't know. Means what will be the pattern in exam? Exam is
Like
on 26th March.
yeah, like it will be communicated to you from the NPTL team. I'm not aware of that actually.
Okay, sir.
Maybe you can raise the question in the discussion forum about asking what's the pattern of exam and all that. They will respond on that
Where I can put this question?
in the discussion forum. There is a discussion forum along with your video, right? There will be a tab called Ask a Question, wherein you
Ask
can,
a question.
yeah,
Okay, okay.
they will respond
Okay,
in that.
sir. Mhm.
Any other questions?
No, sir.
Okay, then we'll go to the next approach. So like maybe we have only 15 minutes. Maybe we'll take up an example in the next week. Now we'll just go through the idea of what this algorithm is.
Huh.
So this approach is like previously we discussed in the algorithm has something called rank, and then we discussed about diversity. Like you pointed out, why not actually use from different ranks, can we use the distance somehow? That is the idea of this particular method. You compare individuals like you with different ranks. Like you do not have the concept of rank directly here. You take an individual, somehow measure both the rank as well as distance, and add both of them to the fitness in a different way. How we do
Okay.
that? So like the algorithm, we'll just see the algorithm first. There are two new estimators or such new terms here. The technique we are using for fitness is the fine-grained fitness assignment. We will see what this method is actually. The second, instead of the distance, crowded distance, we are actually using a density estimator here. This is equivalent
Why
to the
it is
distance.
called fine grained?
Yeah, we will get to that when we see the method. You will understand when you see the method.
And also this strength Pareto. This why
Yeah,
this
yeah.
term?
As you go through the method, you'll understand why we are basically the way you assign the fitness will give you the name of that. We will see that.
Hmm.
In addition to what we were having, like previously we are having some population itself, but now here in addition to population we have something called an archive.
What is that?
An archive.
Archive. Okay.
So it is just some kind of place where you
Some
store all your non-dominated solutions.
okay. It is just some older things.
Yeah, older things, but basically here in our case, it will have some non-dominated solutions inside. Basically, some of the best
Oh.
solutions that you have encountered in your previous generations.
Mhm.
So here inputs will be n is your population size, n bar will be your size of archive, capital T is your maximum number of generations, small t is essentially your counter for your generations. So the first step is once you get all these parameters, the next step is to initialize your population. I'm just denoting P of T, and you have an archive which is an empty set. Initially we start with an empty set for the first generation. Next one, you calculate the value of PT and copy all of this into the archive, and you
Here
update them
also,
like
sir,
that. Yeah.
this population is real numbers, randomly generated real numbers.
Yes.
Okay.
Or you are suggesting you are going to use some. It is actually different from genetic algorithm. I
Okay.
mean, in like if you consider the generalized algorithm, it will be similar. The approach will be similar. You have the same operators. You have some selection, variation. All that will be similar
Hmm.
with
Okay.
minor changes. That's it. But it will be more or less similar to the RGA that we have discussed,
Hmm.
with few additions. Like this archive is a new addition.
Yes, yes.
Even the fourth step is also similar. You just have a loop to iterate over the generations. The next is your binary tournament selection. The only difference here is here you do it with replacement, and you will replace from the archive, not from the
Here
original
what,
population.
sir? First you have generated PT,
Yes.
and then kept the AT as a
Initially
null
null,
matrix,
but then
null,
I kind of
and then you are
copied all the
then
PT to 80.
80. Okay, so both of
Both of them
80
are
and PT
equivalent at the first
equal.
generation. Yeah, for the
Okay, sir.
first generation.
Yeah.
So when you apply, the first step is actually do the tournament selection. Say you pick the individuals from your archive and do the tournament selection. It's the same binary tournament selection we have used in RGA. The only difference is here you pick the individuals with replacement. Like in the
Same SBX will be used here. No,
no,
sorry,
no,
that is
SPX is for
crossover.
crossover.
This is yeah, that is
For
crossover. Yeah.
binary tournament selection, the only difference is here you do with replacement. So in the previous
Okay.
case, when you have 8 individuals, what we did was you
Mhm.
pick 2 individuals. The next time you
Yeah.
pick out of the remaining 6 individuals. So like if you have 8 individuals, you start with
Hmm.
first you pick 2 individuals, then you will be remaining with six. Out of six, you again pick two, then
Yeah.
four you pick two, something like this. But now
Yeah.
here, what we will do is after you are picking two, even in the second case, you pick from the 8 only.
Okay.
Like how many ever times you want, you always pick from the 8. You do not reduce the number. That's the only difference.
Okay.
And like both of these methods will be like the idea is the same. Like if you are taking without replacement, then you have to kind of
Here,
repeat it twice. And the second time,
here we have to
it's
repeat
more.
it, no?
Yeah, here also you have to repeat it, but here repetitions will be kind of 8 times to get 8 solutions.
Yeah.
The next step is the same as the crossover. The variation is essentially a crossover and mutation operator. So we'll be using the same as RGA, like simulated binary crossover and polynomial mutation, to get the PT plus 1, that is your offsprings. Like these are your offsprings. The next is also similar, like even in the previous NSGA we have discussed, like you combine both the parent and offsprings. So A bar of T is essentially your parent solution, like a T equal to initial generation, that will have your P of T. P of T plus 1 is your offsprings. So you are taking a combination of parent as well as offsprings and storing them in your CT plus 1.
So then what do you call this C?
C is your concatenated one, basically your combined parent plus offsprings.
Okay. No,
These are your
what
offsprings,
is
this is
the
your parent.
yeah, parent and offspring? What do you call C?
I'm just saying combined population in the
Combined.
sense combined.
Okay,
Yeah.
okay. Hmm.
Next step is you apply the same dominance depth method we have used previously to get the, or you can use, like basically what we need is how many dominated solutions are there in this combined population. Non-dominated solutions, like NDS is your non-dominated solutions.
Hmm.
So PT plus 1 has n solutions, A bar of T has n solutions. So CT plus 1 will be having 2n solutions.
Yeah.
Sorry, PT plus 1, let me just correct myself. PT plus 1 will be having n solutions. Initially at t equal to 0, A bar of T will have n solutions, but for other iterations, this will actually be n bar solutions. Like we have defined n bar, if you recollect, this n bar is the size of R cube. For initial case at t equal to 0, A bar will have n solutions. So now your CT plus 1 will be having 2n solutions. Out of these 2n solutions, we need to identify how many of them are non-dominated solutions. That is your NNDS. This will give you a number of non-dominated solutions. The next step is essentially to actually get my A bar of T plus 1. A bar of T plus 1 should have only the archive should have only non-dominated solutions, and its size I am fixed it to be n bar. So I need to somehow pick n bar individuals from NNDS. So basically idea is to pick n bar individuals from C of T plus 1 and send them to A bar of T. So A bar of T plus 1. Like this is the idea. But how are we going to do that? If suppose number of non-dominated solutions equivalent to the archival size, then like you don't have any issue. You just copy the entire CT plus 1 into AT plus 1. If suppose the number of non-dominated solutions is less than n bar, then what you do, you take all the non-dominated solutions, put them in AT plus 1.
Sir,
Then yeah,
the CT plus 1 is having size of 2n and AT is having size of n.
yes,
Then suppose you told that if n NDS is equal to n bar, then copy them to AT plus 1.
yes.
So all CT plus 1 is to be copied?
Yeah, basically, no, not all CT plus 1. The NNDS, basically whatever are the non-dominated solutions that you copy
Non-dominated,
into
only
AT
those.
plus 1. We
Okay,
need
sir.
only non-dominated solution inside the archive.
Archive. Okay.
Basically
So
not
archive is
non-dominated,
always having
basically
non-dominated.
like basically the best solutions, not non-dominated. Like to be more precise, like basically you need to have best solutions in A bar of T plus 1. That's it.
Okay.
That will go to the next generation, right?
Hmm.
So if you see the second case, like if your number of non-dominated solutions is less than n bar, like you are having archival size is more, but you do not have that many non-dominated solutions.
Hmm.
So what you have to do is you first take all the non-dominated solutions, add them to A bar T plus, then you will be left with some vacant space. That you don't have any other option. You have to take dominated solutions and fill it because you don't have non-dominated solutions.
So some solution will be non-dominated also.
Yeah, so it will have a combination of both non-dominated and dominated. But it okay.
Hmm.
In addition to these two, there could be other case where your non-dominated solution is more than n bar. Like you have say 10 non-dominated solutions, but your archival size is just 8.
Yeah.
then you need to use a truncation operator to actually select 8 solutions out of the 10 solutions that should go into the archive.
So it is a
the
new
first case
operator?
is easy. Yeah,
No, that
truncation
is
operator
okay, but
is like these two cases require some decision making, right? Here, if you
yeah.
see, copying non-dominated solutions is fine, but you should select dominated solutions. Like to fill the remaining gap, you need dominated solutions, but there are so many
Yes.
dominated solutions. Which one of them will we
Mm-hmm.
choose? So there should be some
Okay.
strategy for that. And if you are having
Mm-hmm.
more non-dominated solutions, then you need to reduce the number of solutions. Then what is the strategy you are going to use for that? Like the second
Okay.
case is quite easy. Like if you think of the truncation operator, basically you have some 10 solutions and you want to choose 8 solutions from them.
Mm.
How will you go about that?
And we take the best one?
No, no. They are non-dominated in the sense because you do not know which one of them is best, right?
Oh,
Like
okay.
if you are saying
Uh,
non-dominated, you just don't know which one of them is best.
okay, yes.
How many I have drawn? Say I have 7 solutions, but
Yeah.
my like NNDS is basically 7, but my
Mm.
N bar is only 4. Which one of these 7? Like you need to select 4. Which 4 will you choose that will actually give you better?
Mm.
Like that is where we kind of come with your diversity. Like I can choose 4 in
Okay.
different ways. If I happen to choose these 4 individuals,
Uh, so we have to select one from out of four, that n bar.
like you need to select 4 out of the 7. Like you have 7 non-dominated solutions, but you need your archival size is just 4. So you need to select 4 out of 7.
Archival size is 4.
Yeah, n bar is 4. My
Mm.
non-dominated solutions are 7. Like if you can see,
Uh,
like all the 7 processes are your solutions,
it
but you
means
need to select
out
4.
of 8, 7 are NDS.
7 are
Out
NDS,
of,
yes,
and you have to select 4.
yes.
Okay, sir.
So if I have, like if you see the arrows, like if I select those 4 individuals, then
Mm.
they are kind of very close to each other. They are not diverse enough.
Yes.
So I have to choose in a different way where something like this, like one of them should point something in the top, one of them should
Mm-hmm.
be at the bottom,
Yeah.
and something like this. Something like this is actually better than the previous one. So like
Yeah.
there is some strategy that we have to follow to use this truncation.
Mm.
Basically, we calculate distance for each one of them and see which one of them, like remove one point and calculate the distances. So how
This,
to remove the point? So from one point we'll calculate all the distances and remove the point which is having minimum distance.
so this is called truncation operation.
That is the truncation operator. That is
Okay.
this the step. So the
Mm.
enhanced archive truncation.
So
We
this
will
is
actually
the,
see the algorithm for that. Maybe that will give
but you have mentioning this complexity.
this one. Yeah.
What is that? Diverse density estimation. It is
Density
q
estimator
square
is to
log.
calculate your distances.
Mhm.
Here we will see because here it comes how the log comes. We will see that. Like I
So
think we are almost reaching the end of the time. Maybe we'll take up it in the next week when you go
here,
through the
sir,
algorithm. Yeah.
when we say,
Mhm.
just a minute, sir.
Yeah, 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 sure.
When we say overall complexity, so
Okay.
here there
Yeah.
are you have given one, two, three.
Yeah, here we will see. Say you have 3 complexities, right?
Yeah,
In of
yeah.
these 3, which one is the worst, do you think?
I think it will be cube, no?
Yeah. So the overall
O
complexity of the
cube.
algorithm will be this one.
So means maximum we have to take.
Yeah, because that will be your limiting step. Like
Hmm.
you should be careful in the sense like see like when the first step is happening, only after the first step you are going to the second step. Only after the second step you are going to
Yeah.
the third step, right?
Hmm.
So whichever is taking the longest time will be the one that is causing the more number of time in your entire algorithm, right?
Yes.
Like it is in series. If it happens to be in parallel, then you have to think in other ways. Say it can so happen that you have to do enhanced archive translation within the density estimator. Like this is not the case. I'm just giving an example. So if this particular algorithm is lying inside this algorithm, then your overall complexity will be multiplication of these both. It is similar to your Taylor series expansion. So like the overall order will be something like q cube plus q square log q. If one is happening after the other, so you are neglecting your basically the terms which are like this is the highest order one, so you are just considering this one and neglecting other ones. If it so happens that one is happening inside other, so like one is happening after the 2 and 3 are happening one inside other, 3 is happening inside 2, then your overall complexity will be something like q square plus q square log q times q cube. Or maybe you can say 2 is happening inside 1 and 3 is happening independently. Then it will be something different. So it will be like q square times, like 2 has to happen each and every time 1 is happening. So it will be multiplication of this plus q cube. So if it is something like this, then your order will be this. This will be the leading term. So that will have q power 4 log q. So that will be your order, worst case complexity. Clear? So we will take up an example next week. We'll close the session. The next week is the last week, right?
Yeah.
Thank you.
Okay, sir. Thank you.